It is 10:04 p.m. I had to come to lab during one of Bangalore rain sessions to do a calculation, which will take 1 hour of computation time. And I realized, hey, there's a YouTube channel that I guess, Susi. So why not upload a video? So today we are going to talk about homoaromaticity because why not? It's a different form of aromaticity that most people have not heard of. Not most people. Well, I guess first year undergraduates till then they haven't heard of it. Then you get to read about it, I guess. So yeah, we disclaimer: if you're here for say CSIR or like previous year questions or something, we aren't going to do that. This is more of an informative video, just so whoever is interested to know about homoaromaticity gets an idea of it. And I mean, it's an interesting concept. Okay, uh, I'll start with a general introduction of what uh, this aromaticity is. Basically, I hope you know this. Basically, you have Huckel's aromaticity, which talks about how there should be 4n plus 2 electrons, pi electrons, and a planar this electron cloud, which is what gives which I will talk about that later. But that these are the two conditions which gives aromaticity. Now, if you have 4n pi electrons, that gives anti-aromaticity. Now, the thing is, why is aromaticity stable is a very complicated question if you think about it rigorously using quantum mechanics, because that is where it comes from. I'll give you an intuitive idea of why is it stable. I'll include an infographic from Master Organic Chemistry, which is where I learned most of my organic chemistry during high school. And this is not a paid promotion. Yeah. So if you see the system of 1,3,5 hexatriene and benzene, because they are very similar, the molecular orbitals are in a ladder-like configuration in hexatriene, whereas in benzene there are degenerate levels, as you can see. And this is why when you have degenerate levels, it reduces the overall energy of the system, which is why it becomes more stable basically. And that is aromaticity. Yeah, that is basically aromaticity. So why is that particular? Why the configuration changes? Why degenerate levels come? Is all quantum mechanics, which is out of the scope of this video. Now, homoaromaticity. If you think about like Huckel's rule, the second point that I said, that it should be a planar system, which is what people don't focus on. Now, the thing is that uh, the electron cloud should be planar, right? That is what it says. It never said that your molecule needs to be planar. You have in aromatic molecules, you have been introduced to systems like that only. But technically speaking, if a pi cloud could exist on its own, which is following 4n plus 2 electrons, it would be a stable system. Don't quote me on that, but yeah, you get the point. It never says that aromaticity is supposed to be all over the all the carbons and all the molecules, all the atoms of the compound. This was the planar part. Now, another point is that when we say aromaticity, your molecules, your pi orbitals are in conjugation with each other. What is conjugation? You saw that alternate pi bond should be there now, which is basically meaning that the pi bond should have an overlap with the other pi bond, which is what allows conjugation, which is what conjugation is. Now, this overlap, the overlap, the better the stability, because it makes sense, right? And yeah, that is all aromaticity. If I take this, I don't know how to edit. I'll probably learn how to edit, but yeah, I hope you can see the molecule. If you say this molecule, now your first guess would be that it is a non-aromatic system, which is what it should be. But you see, it's a 7 carbon system. If you remember the 7 carbon systems, 7 plus carbon systems are flexible. If you see 1, 3, 5, 7 cyclooctatetraene, at first it is a anti-aromatic system, but it changes planarity, changes its configuration, so that it is not anti-aromatic, and it becomes non-aromatic because the conjugation breaks, because the orbital overlap breaks, and thus it is non-aromatic. Now, the molecule that I showed you, if you take this one sp3 carbon out, which was causing non-aromaticity, then it is the other orbitals would come closer, even though there would be a angle strain. They would the main ring electron pi cloud would be formed, and it would be 4n plus 2. So Think about that. Then you have another system like this. Here also you can take both of these carbons out, and it is forming a pi electron cloud with 4n plus 2 electrons, right? This is homoaromaticity. Okay, there's not much to it. So the reason why it is homoaromatic is because it is following the aromaticity rule. It should be called aromaticity, but because of convention, because homoaromaticity is in general like not as stable as aromaticity. So when you are taking the carbon out, that is causing angle strain, that is causing bond strain, which increases the energy. But then it is attaining aromaticity after that, which is reducing the energy. So there's a net reduce in energy, which is why the molecule even chooses to be a homoaromatic molecule. That is the entire theory of it. It's a gain plus loss wala thing. You get the point, right? And same with the other molecule where the two carbons go. So there's more angle strain here. So it would be less stable as compared to the other one. Now, if you see the two molecules, if you see say this molecule for example, uh, if you see the projection of the pi cloud, it is sort of forming like a tropylium ion system, right? Tropylium cation system. That's why it's called homotropylium. That is the name convention. You put homo, and like I'll put some links in the description which gives you more idea of reading the name convention and like what homoaromaticity is in general. So yeah, it's called a homoaromatic system basically. Now this is all what homoaromaticity is, and yeah, another reason why it's less stable is because one is the angle strain, another is that when these two carbons, the other carbons come together, the orbital overlap is not as good as in a normal aromatic system, and that is why it's like less conjugation, less stable, but it is still causing some stability because there is some overlap, there is some pi cloud forming a planar pi cloud. And yeah, that's it. That's what homoaromaticity is. If you have any doubts, I guess you can put it in the comments below, and as I said, I'll put some links in the description so that you get an idea of what homoaromaticity if you want to read further. Yeah.